Talk. We have two postdoctoral associates here at GW. They're both co-founders of JivaJet, which works with plasma power. One of them, Dr. Anmol Taploo, is the CTO of the company, and Dr. Vikas Soni is the CSO. And the title of their talk is Plasma Power Pushing the Boundaries for Earth and Mars. Gentlemen?
Plasma, the fourth state of matter. You must have heard of this word a lot. Not the blood plasma, I'm talking about the fourth state. What's the first and the second and third? Solid, liquid, and gas. Plasma can be as gentle as a healing touch, and it can also be as powerful as a propulsion system. That's what we're going to use here. We're going to harness the power of plasma. Imagine a future where using a plasma engine that's allowing you to maintain satellites at 100-kilometer altitude by utilizing air in the very low Earth orbit. Sounds like science fiction, right? And imagine a jet-like device, lightweight, that helps in treating cancer, antibiotic-resistant wounds, and skin infections. Again, sounds science fiction. My name is Anmol Taploo. I'm the co-founder of JivaJet, and we're going to be talking about our breakthrough innovations. What are we trying to solve through all of these plasma technologies and devices that came out of the work we did during our PhD under the guidance of Dr. Michael Cater? Let's talk about Earth. High-resolution imaging. So this is all verified from our National I-Core customer discovery. We found out that there is a strong requirement of high-resolution imaging, somewhere around 10-centimeter optical imaging. The other thing is space situation awareness. That's very important, especially with the growing concern of war, and we want to also monitor space debris in those altitudes. So space situation awareness is another thing. And the third thing is space debris. So you must have heard of this thing called Kessler syndrome. So we're going to be putting up satellites up there up until we won't have space to put those up there. These are the three main problems on Earth. Let's switch the gears to Mars, because we are at the Mars Summit, Explore Mars and Moon Summit. On Mars, we want to have a Martian architecture which is sustainable and has sustainable mobility. And also, we want to come up with some innovative ways to make oxygen from the carbon dioxide-rich atmosphere of the Mars. What are our key solutions? Before I try to progress further, I want to show you how our plasma jet looks like. This is our atmosphere-breathing plasma thruster. You can see some of the plasma plume images in the purple that indicates nitrogen plasma. What it does is it uses the atmosphere gas. So if you're on Earth, air. If you're on Mars, it's going to use CO2, and the other planets, let's say hydrogen, etc. It's going to ionize that gas, and it's going to create a plasma. The plasma is then accelerated using electromagnetic fields. And that accelerated plasma is going to create thrust and maintain your satellite or your spacecraft in the orbit. What's our most unique selling point? The most unique selling point that I discovered after working on this for the last 5 years of my life is high thrust-to-power ratio. When you're talking about plasma propulsion systems, thrust-to-power ratio is very key. It's an important term. And we are achieving orders of magnitude higher thrust-to-power ratio, which will allow us to scale this up and scale this down. If you're using atmosphere gas in the low Earth orbit, you're not carrying any propellant tank with you, which means you're going to save a lot of weight of propellant. You are also going to save a lot of refueling cost. So that's the whole idea, in situ resource utilization kind of concept. And it allows your propulsion capabilities in very low Mars and very low Earth orbits. And that can be used by lowering the altitude of the satellites, and satellites will be maintained in those drag-induced orbits with our technology, and that will enable you to get high-resolution images, improve communication, and most important thing is your propellant, in this case, which is air or CO2, is also your drag source. So if your satellite goes out of control, what's going to happen? Your satellite will automatically re-enter, making space more sustainable and self-cleaning. And one and last most important thing for Mars, because we are talking about Mars here, it also actively not just produces propulsion system, it's not just do propulsion, but it's also actively converting CO2 to oxygen, which means that we can actually use it for dual case purpose, electric propulsion and oxygen generation. And that data is shown you see the graph on the top. We have that oxygen peak generated in our spectrum, and we found out that this oxygen peak, with some estimation, we found out that the oxygen generation from this technology is comparable to the MOXIE, which NASA has. Let's imagine. We're going to deploy this in sun-synchronous orbit in the satellite in coming years. And then we're going to be able to do on-demand imaging. Once we do high-resolution optical on-demand imaging, whoever the customer is, whether it is DoD or commercial, the satellite will, after the end of the mission, the satellite, you just turn off the thruster, it automatically re-enters and burns up upon re-entry, making it sustainable. And on Mars, one, because of high thrust-to-power ratio, and also because of oxygen conversion, you can use it for 3 purposes: generating oxygen for the Mars habitat, utilizing it in the Mars rovers or like vehicles, and also you're making like a network around Mars with Mars atmosphere breathing thrusters and satellites. Now I'm going to shift the gear to plasma medicine, and I would like to invite Dr. Vikas Soni, founder of JivaJet.
Thank you, Anmol. So thank you, Anmol, for the introduction. I'm Vikas Soni. I'm the founder of JivaJet. So let's switch gears, and I'm going to talk about some stuff that we do in the lab that's very cool stuff. So as Anmol mentioned, cold plasma is the 4th state of matter, and we are trying to utilize this for space medicine and space propulsion as well. So unfortunately, the slides are not moving forward, so I'm going to see. OK, so before I jump into our tech, there are major problems. Let's talk about the major problems in space, which is one of them is space radiation. And can you imagine 6 months in space is equivalent to 1,000 chest X-rays? That's a lot of radiation, and it's highly significant. And also, it causes DNA damage, increases the chances of neurodegeneration. And also, cancer drugs expire because they are not that potent, and they have a tendency to degrade. And there's only limited amount of drugs that you can carry in a payload. So what is the solution? The solution we offer is cold atmospheric plasma. It is an adaptive technology that can adjust itself based on the tumor profile and change the intensity of its plasma plume. It generates reactive oxygen and reactive nitrogen species that's therapeutic for cancer because there's already high level of reactive oxygen and nitrogen species in cancer cells. It treats different types of cancer. It promotes rapid wound healing. And it's also the underlying technology is FDA approved. That is a spin-off from GW. So to summarize, it's basically a lifesaver that looks like a lightsaber. It's topical, non-invasive. It's patented. And there is no reliance on any drugs that you carry on the space missions. So as you can see here, I'm going to show you some data on scanning electron microscopy on extreme top left. That's our untreated control sample, and bottom row is treated with plasma, and the cells basically cooked like an omelet. And at the bottom, you see real-time live imaging of brain cancer cells. On the left is untreated cell, and on the right is treatment of plasma for just 60 seconds. And you see those blebs and blebbing-like structures and nuclear fragmentation. That's a hallmark of apoptosis. In simple language, cell death. We've also tested this in preclinical models of mouse. We implanted tumors from patients and grafted in skull of mice, and did a non-invasive treatment using the plasma just for a single time. And our lab was the world's first lab to do this treatment in a non-invasive way by exposing plasma and hovering it over the skull of mouse with just 60 seconds of plasma exposure, and there was 79% tumor inhibition. So I'm going to switch gears to the second major problem that we have in space is wound healing. Astronauts go through wound healing issues. Imagine you're out there in space and you get a small cut. No big deal, right? On Earth, it's not a big deal, but in Mars, everything is just slow. It's microgravity, there's less oxygen, there's less blood supply, no nutrients. So the platelets do not arrive on time to the wound and they not heal properly. And I'm showing an example of an astronaut using a 3D printed bandage, but that's also limited because it lacks infection control, and there's only limited amount of stuff that you can carry up there. So what we are offering here is, again, cold atmospheric plasma device that we have, and I'm showing you results from the FDA. I was working at the FDA, and on the left is Staphylococcus aureus that's resistant to the treatment. And after 5 minutes of plasma treatments, you can see the holes and perforations on the top row. And it is a dual-purpose treatment, so you also see wound healing. So in diabetic mouse and wound healing preclinical models, after just 1 minute of plasma exposure, stained by the green arrows pointed there, you can see the wounds healed, and there was formation of new blood vessels also. So it basically acts as a dual-purpose treatment. It eradicates antibiotic-resistant bacteria and also enhances and accelerates wound healing. So let's talk about something that's we have spoken about propulsion, we have spoken about cancer, but let's talk about plant biotech in space. So we have shown in the lab that our technology can actively generate oxygen from carbon dioxide, and that's going to be huge breakthrough in Martian environment because 98-95% of Martian environment is carbon dioxide. So what we are trying to do here is plasma has been already proven, and it's more than 2 decades of research that plasma is used in seed germination. What it basically does is after exposure to plasma with the seeds with plasma, it basically removes the coating and it absorbs more water and activates phytohormones, basically hormones that are used for growth. So it enhances seed germination, and it can be really useful in generating plants up there for farming and food agriculture. It basically develops some sort of reactive species that contains the seeds and then activates some hormones to develop these plants. So it can function under harsh environments, Martian and lunar environments. We have not tested this in microgravity yet, but it supports the oxygen and food production there. So with that being said, we are here to harness cold atmospheric plasma technology to help space medicine, and our mission is to generate some technology that can be used up in the space. And with that being said, I'll leave you with the spirit of our company that's smart, scalable, and science. Thank you.